Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 8 on secant and tangent lengths. So we've been playing a lot with secants and tangents in the last few lessons, but we've really concentrated on the angles that they create. Today what we'll be doing is we'll be looking at their lengths instead of just their angles. So let's get into it right away. All right, the lengths of secants. Now in the last few lessons we've seen how the angles created by secants, tangents, and chords relate to the arcs that they intercept. In this lesson we will see how the lengths of secants and tangents relate to one another. All right, so let's take a look at exercise number 1. In the diagram of circle O, secants PAC and PBD have been drawn. It is known that PA is 3, AC is 5, PB is 4, and BD is 2. Find each of the following products. Great. Now this isn't going to be very hard, right? If I'm just asking you to find some products, it should be simple enough. But what I'd like to do real quick is just label stuff on the diagram, right? We've got what? We've got PA is 3. All right. We've got AC is 5. All right. We've got PB is 4. And we've got BD is 2. And let's just kind of give a nod to the fact that, of course, we could add those two together to find that PC is 8 and add these two together to find that PD is equal to 6. Right? That's simple enough. Now, what I'd like you to do is pause the video right now and just find each one of these products. It should be simple enough. You just got to be careful about what's what, and then we'll fill them all in. All right, well, easy enough, right? PA times AC is going to be 3 times 5, so that's going to be 15. PB times BD is going to be 4 times 2, that's going to be 8. PA times PC, that's going to be 3 times 8, which is going to be 24. PB times PD is going to be 4 times 6, that's also 24. AC times PC is going to be 5 times 8, which is equal to 40. And BD times PD is going to be 2 times 6, and that's going to be 12. All right, so not difficult here. But we want to observe something. Take a look at letter B. Circle the pair of products above where the two products are equal. How would you describe the line segments in each part of the equal products? Okay, so I think this is pretty simple, right? When we look at these products, there are only two that are equal to each other. That's PA times PC and PB times PD. All right, now what do we see here? Well, let's go highlighter, right? I like the highlighter in geometry. Just for a moment, right, PA is this segment, PB is this segment. Now it's a little bit harder to do the other two because they encompass these segments, right? PC is this segment, and PD is this segment. Okay, whoops, still didn't get it. Let's try that again. There we go. So, what are we really seeing here, right? It appears that when we take the segment of the secant that is outside of the circle and we multiply it by the length of the entire secant, and then we take the length of this secant that's outside of the circle and multiply it by the entire length of the secant, then we're getting a consistent product. There's no other situation where that's happening, right? Now, by the way, this might remind you a little bit about when two chords intersect inside of a circle, right? The product of the partitioned segments always stays the same. Except here, if that was the case, we might get something like PA times AC equals PD times BD. That's not happening. PA times PC is equal to PB times PD. And actually, let's write that down right here. PA times PC is equal to PB times PD, and it looks like exterior times the whole is equal to exterior times the whole. And actually, let me put times the whole there. Okay? And interestingly enough, that is always the case. The secant segment length theorem. Remarkably, what we just observed in the first exercise is always true of secant segment lengths. So let's kind of summarize this in the secant segment length theorem. If two secant segments are drawn from a common exterior point, then the product of the length of one secant with the length of its external segment is equal to the product of the length of the other segment with its external segment. All right? So it's kind of interesting. And again, we're going to prove this, obviously, a little bit later on. But if we've got two secants that are drawn from a common exterior point, then if I take the entire length and I multiply it by its exterior segment, that will be equal to this entire length times its exterior segment. All right? That's a little bit hard to remember, but we've had quite a few theorems in this unit that we have to memorize. So let's take a look at it in exercise 2. It's pretty easy to apply this theorem. In the diagram of circle O shown, it's known that AB is equal to 6, BD is equal to 2, and AC is equal to 4. Determine the lengths of the following, diagram not drawn to scale. Letter A, determine the length of segment AE, and letter B, determine the length of segment CE. All right, well, let's work through this one together. Let's get all the lengths up there that we've been told, right? We've been told that AB is 6, that BD is 2, and that AC is 4. All right? Now, what our theorem says to us is that if we take AB, the exterior part of that one secant, and we multiply it by the entire secant length, AD, that's going to be AC times AE. Now, what's kind of great is, of course, once we know that's 6 and that's 2, then clearly all of this is 8. And so we can say that 6 times 8 is equal to 4 times AE. Right? That's easy enough. 6 times 8 is 48, is equal to 4 times AE. Divide both sides by 4, and we find AE is equal to 12. And of course, letter B is very simple, right? Once we know that this entire thing is equal to 12, then of course CE simply must be 12 minus 4. I should do this. CE is 12 minus 4, so CE is 8. All right, a very, very easy theorem to apply, a little bit tricky to kind of understand, and again, we'll prove it in a little bit, but sometimes the proof doesn't particularly help you understand it, it just helps you prove it, right? Helps you have confidence that the theorem is actually correct. All right, now, let's take a look at the secant tangent length theorem. The previous theorem can be extended to where a tangent and a secant have been drawn from a common exterior point. It may seem like it's a different theorem from the last one, but it's really the same form, and I'll explain why in a moment, right? Let's take a look at the secant tangent length theorem. If a secant and a tangent segment are drawn from a common exterior point, then the product of the length of the secant with the length of its external segment is equal to the square of the length of the tangent. So in other words, let's take a look at this, right? If I've got this secant and I've got this tangent, I'm now saying that PA times PC is equal to PB squared. And I actually make the claim that this is just the same theorem as the last one, right? The last one said if I take the exterior portion and I multiply it by the whole, I'll get the exterior portion times the whole. The difference is that for a tangent, the exterior portion is the whole, right? So exterior times whole is equal to exterior times whole, right? There is no interior point of a tangent, right? So I just get PA times PC is equal to PB squared, which sounds a little bit funny because it sounds like I'm talking about a peanut butter sandwich. All right, let's take a look at exercise number 3. In the diagram of circle O shown below, a tangent is drawn from point A to the circle at point B. Secant ADC is also drawn and has a length of 12 units. If AD to DC equals 1 to 3, then do the following. Determine the length of AD. Great. All right. So first things first, without using the theorem that we just looked at all, we've got to be able to figure out the length of AD, otherwise there's no way we can use this theorem. We've got to know the length of that exterior segment. That's all going to be about the fact that this entire segment has a length of 12 units, and the ratio of AD to DC is 1 to 3. So see if you can figure out what the length of AD is. It's pretty easy. Well, there's a couple different ways. One way is sort of what we've been doing for a while with these ratios. I could call AD x, I could call DC 3x, I could say x plus 3x is equal to 12, etc. But I also want you to recognize something a little bit more basic than that. If the ratio of AD to DC is 1 to 3, then the ratio of AC to the ratio of AD, I apologize there, AD to AC has to be 1 to 4, right? This gets back to when we partition line segments, right? If this is 1 to 3, then this must be 1 to 4, 1 to 4, which means that AD is 1/4 of the length of the entire segment, right? AD simply must be 1/4 of the length of AC, which is 1/4 of 12, so that's equal to 3, right? And then it kind of makes sense, right? That's 3, that's 9, and there's your 1 to 3 ratio, right? 3 to 9 is the same as 1 to 3. So AD is equal to 3. Now, they want me to do, in letter B, to determine the length of AC. Wait a second here. How does that make sense? Okay. ADC, AC, AB, the length of ADC is also drawn and has a length of 12 units. Yeah, I think that was meant to say DC, all right, because the length of AC is 12 units. So the length of DC, not AC, DC is just going to be 3 times AD, which is equal to 3 times 3, which is equal to 9. I'm like, wait a second, we already know the length of AC. That seems a little bit redundant. There we go. Anyway, now letter C. Determine the length of AB. So finally we have an application of the theorem, right? And the theorem, very simply put, right, is that AB, its length squared, is equal to AD times AC, right? So AB squared is going to be 3 times 12, which is 36. And now AB will be the square root of 36, which is equal to 6. All right, and that is it, right? Simple enough. And again, I do want to point out this has the same form as what we've seen in the past, or what we saw in the previous theorem, which is the exterior portion times the entire length is equal to the exterior portion times the entire length. It just happens that with a tangent, those two are the same. All right, sorry about the mistake there in letter B. We'll get that corrected for the book. Now, let's prove that first theorem. We can prove both segment length theorems using similar triangles. In the next exercise, we're simply going to prove the first one, and guess what? You get to prove the second one on the homework. All right, so let's take a look at exercise number 4. In circle O below, secants PAC and PBD have been drawn from point P. We wish to show that the equation PA times PC is equal to PB times PD will always be true. Auxiliary line segments AD and BC have been drawn, and they're the ones that are in dashed. All right, so, right, I've got this just, 2 secants drawn from an exterior point. All right, I've got my auxiliary lines thrown in there so that I can get some triangles going. Notice how much involves triangles when it comes to circles. So letter A. Why must angle C and angle D be congruent? So I claim that that angle and that angle, they have to be congruent. Pause the video now and see if you can figure out why. All right, well, it's really simple. They intercept the same arc. right? Both of those two angles are inscribed angles that intercept arc AB. All right. Now that means that they're both half of the measure of arc AB, but I don't really care about that. That's kind of irrelevant for what I'm doing here. We have a theorem that says two inscribed angles, which C and D are, that intercept the same arc have the same measure. So they both intercept arc AB. All right, great. So wonderful. So now, right, I know that these two angles are equal. Letter B. Explain why triangle PBC and triangle PAD must be similar. All right, so now I've taken these two triangles, PBC, drawn it here, and PAD, drawn it here. My claim is those triangles have to be similar. Why is that? We already know that these two angles are congruent. See if you can come up with an argument. Pause the video now. All right, well, it's really simple, right? We already know that angle C is congruent to angle D. Whoops, let's not do lowercase. Angle D from A, right? And I could, if I wanted to make it more formally, I could say angle C is congruent to angle D because they both intercept the same arc. Simple enough. But I could then say that angle P is congruent to itself, right? It's a shared angle. Those two angles are equal to each other, right? And that's the reflexive property. So we now have the angle theorem to show that we've got these two triangles similar, right? And once we have similar triangles, it's just a small step to get us the rest of the way. So let's take a look. Letter C. Using the similar triangles from B, set up a proportion involving the segment lengths in the theorem and write it in product form. Now remember, what that theorem said, right? That theorem said that PA times PC was going to be PB times PD, right? That's what we're driving towards. This is what we're trying to prove. I'm not starting with this, right? Now, what I know, right, is that angle is congruent to that angle, this angle is congruent to that angle. So I know those two triangles are similar. So the first thing I can do is I can say PB divided by PA is equal to PC divided by PD, right? So PB divided by PA is PC divided by PD. Now, it would be very understandable if you said, well, why not get BC and AB involved? And the only reason I'm not getting them involved is that they are not part of what I'm trying to prove, right? They're not part of what I'm trying to prove. And that makes sense because those were really those two auxiliary lines that I threw in, okay? So let me come back down here, and of course, once I have that, if I was writing this up in a proof, I might say as my reason, corresponding sides of similar triangles are proportional. But now I can just simply cross multiply, and I can say that PA times PC is equal to PB times PD. And there it is, right? Simple enough. But what's so cool about it, right, is that when you have a picture, right, when you have this kind of scenario that's going on like this, right, you don't really see in any way why similar triangles would even be involved. But they're there. They really are. Once you draw these two line segments in, those auxiliary line segments in, then you have these two similar triangles, which establishes that relationship. And whether those lines are drawn in or not, that relationship then still holds. All right, let's wrap this up. So this was actually our last lesson, not in Unit 9. We've got a few lessons to go in Unit 9, 4 to be exact. But it was our last lesson to really look at the way that the lengths of secants, tangents, chords, all of that relate to one another, as well as the last time that we see how the angles and the lengths and all of that relate to one another. All right? And we really kind of saw this basic premise, this idea that if we take, whether we're talking about tangents or secants, if we take the portion of the tangent or secant that's exterior to the circle and multiply it by the entire length of the secant or tangent, that product is constant. And because of that, we can use it to solve for a missing part if we've got all the other parts present. All right, I want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.